And this one's not as pretty as yesterday because I didn't have time. Gay-Lussac. You want to take a guess where he's from? Of course. He's a French physicist and chemist who came up with his own law. The law of Gay-Lussac, much like Boyle's law, is based on a constant. Okay? What's great about the Gay-Lussac's law, if you can do Boyle's law, his constant is set the exact same way. He is connecting, what did you yesterday? Pressure and volume. Okay. Today we're doing what I say we'd all be comparing. Pressure, volume, and what's the third thing we're going to compare? No. I said yesterday, we're not dealing with this today because it's not changing. What was the other one? Temperature, Celsius. All right. So Gay-Lussac, Gay-Lussac dealt with pressure and temperature. Okay. And so you had a pressure and you had temperature was equal to your constant. Okay. So, again, like we did yesterday, let's set it up in a way where we have 12 divided by 2. So 12 is my pressure, temperature's 2. So what's my constant going to be here? 6. Okay. So, like we did yesterday, let's change pressure. Let's change pressure to say 6. So if my pressure changes to 6, what's my temperature have to change to keep my constant the same? 1. So going from 12 to 2, what happened to my pressure? My pressure went down, and my temperature did what? Went down. Okay, we do it once, that's good. You got to do it multiple times to make sure that it is correct. So let's say, change colors up for you. Come back. Let's say my pressure is now 24. I still want it to be what? 6. So my pressure is 24, my temperature has to be 4. So my pressure did what? Increased. So my temperature increased. So now we're to this thing where they both are going up. So that's what we call directly proportional. So pressure and temperature, they go hand in hand. Which would go back when we talk about a gas. What's going to happen when you heat a gas up? What happens to those particles? They spread out. They speed up. And as they speed up, they're going to start bumping the edges of that container more. And what do we call that? They hit the edge of the container? Pressure. So the faster those molecules go, the greater the pressure is. So the hotter it gets, the more pressure that you will see in that vessel or in that container. So, let's now look how this works. Like we did yesterday, P1 over T1 is equal to P2 over T2. Now, this can be scary to people. Why is it scary looking? They're dividing. Who here likes division? Fractions. You mentioned that to a middle school student. It's like, oh my God, But we'll get to the division, multiplication. So what we're going to do, because when I start doing it here, I start some inverses. I have to have like 1 over t and then invert it. It can be done, but if I just multiply, cross multiply, I end up with P1 T2 equals P2 T1. Because the day of the test, or when you actually need this, you're going to say, I'm supposed to flip it here, put the inverse here, without the division. So with this, it becomes much simpler. P1 T2 equals P2 T1. And so this is an abridged version or an altered version of Gay-Lussac's law. Still gets the same answer. So P1 T2 equals P2 T1. So just like yesterday, if I'm going to find one of these variables, I want to find P1. I'm going to rewrite the other side first. So P2 T1. And then how is T2 connected to P1? Multiplication. So to get rid of multiplication, I divide. And that ends me up with T2. All right. Take 35, 40 seconds. Write the other 3 variables. Just make sure you know what you're doing. You're just not just copying me down. You're going to rewrite the other side and then divide by the variable it's connected to. All right. And then you have your P2 equals P1 divided by T2 divided by T1. I said that wrong, but I wrote it correctly. And then I got T1 equals P1 times T2 divided by P2. So every time we work with these gas laws, it's always going to be a division problem that starts from multiplication problems of formula. Same layout every single day. The only thing that's changed today is what? From Boyle's law to Gay-Lussac's law, what's the only thing different from this layout? Temperature. Now, yesterday, what was my rules on units? They just have to be the same. It could be atmospheres, it could be millimeters of mercury, it could be kilopascals, it could be cc's, milliliters, kiloliters, centiliters. It didn't matter what it was as long as they were the same. Same holds true. The volume, the pressure, unit must agree. Don't matter what they are, as long as they agree. And then you have the temperature. This is your only must. Your temperature must be in Kelvin. The reason being these ratios only work off that scale. So you'll get smaller numbers than you're supposed to if you don't work in Kelvin. Most of the units I give you are going to be in Celsius. So Kelvin is equal Celsius, what? Plus 273. So there's every temperature. If it's not in Kelvin already, you need to add 273 to it to put it into that to that scale. That's the only thing you got to remember. And I will see that on tests where people Excel to our worksheets, come over, you understand why you got the wrong answer. It's because usually you're not in Kelvin. All right. What is the pressure change of a volume of gas at 760 millimeters of mercury, which is heated to 40 degrees Celsius from 15 degrees Celsius? All right, so what's your first step? What I told you to do? Get everything labeled first, then we'll start changing stuff. All right, so this 760 millimeters of mercury, what's that a measurement of? Pressure. Okay, so we'll say P1 is equal to 760 millimeters of mercury. Now, I like this problem because it teaches one skill that I really want to hammer home. So, at this pressure, what temperature is it? Is it 40 degrees or 15 degrees? This is how most people, or a lot of people, will make this mistake. They'll say, okay, these are the closest in the sentence, so they must be together. But look at the way it's worded. It's heated to 40 degrees from 15 degrees. So where did it start at? 15 degrees. So T1 equals 15 degrees, and you can go ahead and add your 273 to it. And that'll be your actual T1. So that makes these 40 degrees, your T2. I'll go ahead and add your 273 to it. And then what am I looking for then? Pressure change, so your P2. All right. So, you don't have a calculator already? Go ahead and get it. They're up beside Nicole's head. Make sure that, again, you add your 273. Before you do anything, add your 273. Get numbers, and then plug your numbers in. And remember, you got P1, T2 equals P2, T1. So you would have, Give you a couple more seconds. But looking at your question, how many digits should your answer have? All right. You look here. This is 3 sig figs. 3 sig figs, 3 sig figs. So your answer should have 3 sig figs. Calculator gives you this huge answer. You should round that to 3 sig figs. So it's going to round to what? 826. 826 is less than 1,000, so I'll keep it at that. And then what unit would it be? Oh, Celsius, Kelvin. What am I looking for? Pressure. In this problem, what is pressure measured in? Millimeters of mercury. Let me show you one way you could have figured that out. You know algebra. Kelvin cancels. I'm left with millimeters of mercury. Okay? Any questions? Just be careful on that. Be careful with your units. Be careful adding your 273. Okay? I think you got it. I'm not going to waste your time doing another practice problem when I could just let you go.